So let's start about discussing why do we even have to learn about software engineering in the first place, to give you some motivation about what this course is about. So for a number of lectures in the beginning, I will be talking these words. The goal is to think before you code. So this might seem pretty obvious, but a lot of people actually miss this when they are developing their applications. So for a number of lectures in the beginning of this course, we will be repeating these words: think before you code. And I'll start with this example. So if you're building a Hoover Dam, which is an incredible thing, as an incredible amount of work, and it's a pretty hard work, and building a Hoover Dam or any other engineering structure has to do with civil engineering, which is an area of engineering required to build such structures. And civil engineering is hard. It has incorporated centuries of developments in construction, hydraulics, electrical engineering, material science, and many other areas. But one thing that is easy about civil engineering is that it is, materialized. Its product is, usual material, concrete product. If you were building this structure and you got halfway through building it and you saw a huge crack in the concrete, you would physically see it and be able to identify and fix it. And if you, screwed somewhere up, and if it was completely done and water were flowing straight through the middle, people would know it's not working. So this is not the case with software. So when you're thinking about software, this is not the case. A computer program does not have a physical manifestation apart from the little charges in your computer memory that you can see anyway. So producing a software application is relatively simple in concept. You take an idea and turn it into a useful program. The very fact that the software is a non-physical entity makes it so much harder to build. So this is why we have such titles as the coming software apocalypse, that may be somewhat paranoid but nonetheless non-groundless way of putting up the fact that unfortunately for projects of any real scope, there are countless ways that a simple concept can go wrong. So to give you just a few examples, so programmers may not quite understand what users want or need, which may themselves be two separate things. And thus, the programmers basically build the wrong application. One of the famous recent examples would be the largest movie resource on the Russian internet, Kinopoisk, that was restarted on October 8, 2015, which provoked actually a scandal. So the new design and interface were criticized by both users and founders of the service. So Yandex, which owned the portal, had to basically return the old version, while the new one was finalized for a little while. So as you can see, here's an example where programmers do not really understand what the users really wanted or needed. And as an example is that, well, the problem with software is that some of the programs are full of bugs, and some of the programs may be frustrating to use and impossible to fix, and they can't be enhanced over time. Well, this is a somewhat exaggerated example, but on June 4th, 1996, and only 30 seconds after the launch, the Ariane 5 rocket launched from the Canaveral, USA. So it basically began to disintegrate slowly until its final explosion, and here's why. So the report says the greater horizontal acceleration caused a data conversion from a 64-bit floating point number to a 16-bit signed integer value to overflow, and cause a hardware exception, efficiency considerations has omitted range checks for this particular variable, though conversions of other variables in the code were protected. The exception halted the reference platforms, resulting in the destruction of the flight. So as you can see, these are a great example where, untested software caused tremendous harm and tremendous losses. So this is one example where you pretty much have a difficulty in releasing software like this. So an absolutely perfect application could even be killed by internal business politics or market forces. An example would be Chrome apps. For a little while, web browsers were believed to be starting to replace actual operating systems, meaning that you should be able to use apps on them. So maybe you have heard of Chrome OS. And if you're not familiar with Chrome apps, so they're apps that you can install in Google Chrome browser that work similarly to apps that you'd launch from your desktop, like Read It Later app, Pocket. But they aren't widely adopted, so Google said that approximately 1% of users on Windows, Mac, and Linux actively use Chrome packaged apps all the way back in August 2016, when it first announced plans to wind down support for the platform. So this is one example of a project where market forces basically do the job and act severely harmfully to the actual software project. And in fact, now a number of projects has been shut down by Google. So don't think this only happens to losers or things like, or people like that. So this is a list of 41 of the projects that Google has shut down during the last 8 years. So you can click on the link here and go see them. Those are some of the difficulties that developers encounter when working on software engineering projects. So what is, essentially software engineering? So software engineering is more or less an organized and analytical approach to the design, development, use, and maintenance of software according to Rod Steffen's definition from the book Beginning Software Engineering. So software engineering includes techniques for avoiding the many pitfalls that otherwise might send your project down the road of failure. It helps you meet milestones on schedule and produce a finished project on time and within budget. Perhaps most important, software engineering gives you the flexibility to make changes to meet unexpected demands without completely obliterating your schedule and budget constraints. In short, software engineering lets you control what otherwise might seem like a random whirlwind of chaos. The process and the challenges that software engineering is trying to address may be explained by a following example. So let's consider someone willing to build a private house, a dacha, if you will. So if you were to build a house, you will probably reach out to a builder and tell about your needs, like I need 2 bedrooms, I need a bigger raid room, I need a room in the basement, and so on and forth. And builders may give you some options, then you will have to do some analysis and come back with your choice. In the end of this phase, you will figure out exactly what you're looking for. Then builder is going to go back and going to create a floor plan. And then he's going to show you the floor plan and you make some adjustment. And once that is done, builder is going to create a detailed map or detailed plan about where the foundation is going to be, where the electricity is going to be, where the plugs and the plumbing is going to be. And then they're going to start building the home. And as they're building the home, they're going to call the inspection people to come and inspect the house. For example, let's say the foundation is done, then they're going to get the foundation approved. When the plumbing is done, they're going to get the plumbing approved, and so on. And once the house is ready, he's going to call you to say whether you like the house, is that what you expected? And once you approve it, then you're going to start, staying in that house and living in that house. And of course, there comes the maintenance of the house. Let's see how software development is similar or different than this. So when you're building a software similar to building a house, you're looking at requirements, or you're looking at what exactly you need to build. And during that time, you will do analysis of different options, or you might do a prototype and show it to your customer and just say, is this what you're looking for? But at the end of this phase, you have exactly a vision of what you're looking to build. Then comes the architects and the software developer. They're going to design the system. They're going to architect the system and say what are the different components that they need to build and how they're going to work together. And once the design is done, they're going to start coding, and they're going to start unit testing. So each of the sub-teams are going to start building their components and test it. And once all of the components are ready, they're going to bring all of the components together and do integration testing and functional testing. And when the software is ready from the developer point of view, then they're going to invite the user, then we'll do a testing called UAT, or user acceptance testing, in which a user says, yeah, that's what I was looking for, or no, this is not what I was looking for. And then once everything is done, then the software goes into production and gets deployed, and when it's released and gets maintained. And so this is called, a vanilla waterfall model of the software development process. As industries started to use this method, they ran into a number of issues. For example, they found that it's very difficult to predict the market changes 1 year or 2 years ahead, and it's very difficult to predict the requirements, and sometimes user needs are not certain or change over time, and it's hard to predict what a user will or will not like. And since this cycle is a year or 2 years, it's possible that the developers or the architects misinterpreted the requirements, and that misinterpretation will go undetected all the way to design, implementation, verification, and similar integration issues between different components go undetected for a year while the software is being developed. So as these and other issues, such as the need to respond to technological change and keep high quality level, were coming up, other variants for the development processes started to evolve, such as incremental, spiral, unified process, or agile models and frameworks. So now we have quite a number of process models and mindset and approaches to develop software. The basic idea behind most of these models is that instead of building the whole 1 year cycle, you can build in short cycles. So you can define a little, you build, you test, and you learn, and then again you just keep doing this. So that way you can adjust to the market quickly, and then you're learning from the users quickly. And so the change became a norm, because after every cycle you may have a change, and then software industry has to learn how to respond to this change quickly and confidently. And so a number of ideas like building more solid engineering, more solid requirements, and developing incrementally using agile processes, and a number of risk mitigation strategies have been introduced. And of course, the idea of continuous integration, and where a developer who is building the code, as soon as he commits the code, or as soon as he finishes the code, it's integrated with all the other components of that software. And automated testing and formal QA has been developed for software engineering purposes. So As you can see, software engineering is quite a difficult thing to do. And in fact, software engineering is one of the most complex things that humans have ever done. And that has to do with uncertain or changing user needs and volatile market trends and requirements changes and technological advancements and many other problems. And in fact, around 20% of projects fail according to the resource called the Catalog of Catastrophe. So software engineering is a set of techniques and a set of tools and a set of methods that basically focuses on removing the typical pitfalls of software development projects. So they do this by introducing solid processes and iterative processes and risk mitigation strategies, but also on the technical side by introducing formal quality assurance and continuous integration and testing, and also introducing more solid deployment and cutover strategies. So this is why it's useful to learn something about software engineering to solidify your software engineering processes. So you're commonly encountering this term software development lifecycle. So in many ways, software engineering is a lot like other kinds of engineering. Whether you're building a bridge, an airplane, a nuclear power plant, or a new and improved version of Sudoku, you need to accomplish certain tasks. So no big project can succeed without a plan. So for example, you need to make a plan and follow that plan and overcome expected obstacles and somehow verify that you are going the right way, and finally give your results away to customers. Meaning that we need an organizational paradigm that will help you guide your team towards the goal, understand your status and track progress, or make corrections in your processes. And so all engineering projects have some form of a life cycle. So when you're building a software-intensive system, this life cycle is referred to as the software development life cycle. So software development life cycle is a commonly accepted series of phases that software systems undergo, and it's useful for managing a planned and controlled development effort. The biggest advantages are that it provides some level of control of the development process to ensure that the ultimate solution is consistent with the original requirements, and to ensure that the design process and testing process leading to release of a solution is sound and well managed. It also has the advantage that it is a repeatable process. So if you develop something with a given SDLC and a similar project comes along, you should be able to use the same process with some level of confidence or success. The biggest disadvantages of SDLC are that it does not work well in an environment where there is some level of uncertainty, and it also can create a lot of unnecessary bureaucracy and overhead. So it is designed around a situation that emphasizes planning and control, and it isn't well designed to encourage creativity and innovation as the project is in progress. So for those reasons, many projects are moving to a more agile and adaptive incremental development process approaches, which are nevertheless a variant of a sequential SDLC. So let's get ourselves a bird's eye view on the phases in the life cycle. One of the first steps in a software project is figuring out the requirements. To this end, the following questions arise. Who's the customer? The customer is someone who will be using the finished software. Sometimes it's easy to tell who the customer is. For instance, if the faculty order a web conference software, then the faculty are the customers. However, if you're rolling out web search, Understanding who the customer really are is difficult. You want to figure out what the customers want and what the customers need. Wants and needs are not always the same. For instance, if I'm hungry, I might want a burger, while what I really need is a salad. So revealing customer needs may or may not be easy depending on how well defined the customer's needs are. After you determine the customer's needs, you can turn them into requirements documents, such as the software requirements specification. Those documents tell the customers what they will be getting, and they tell the project members what they will be building. After you know the project requirements, you can start working on the high-level design. The high-level design includes such things as decisions about what platform to use, such as desktop, phone, or even watch. Which data design to use, such as direct access, second tier, third tier, and interfaces with other systems. At this point, components and their separation is agreed upon, so that the construction work can later be effectively dispatched to teams. Some of the preliminary technical design occurs here too, like the interfaces between the modules being agreed upon. The core difference between the architectural and the construction processes is that while architecture should be agreed upon universally, actual development may proceed in development groups, rather smaller than the whole team. This is because typically features do not require much more than a few people to design, implement, and test. The low-level design includes information about how a piece of the project should work. The design doesn't need to give every last nitpicky detail necessary to implement the project's major pieces, but they should give enough guidance to the developers who will implement those pieces. So typically we use diagrams and sketches to basically transmit the low-level design to our developers. After you have created the high and low-level designs, it's time for the programmers to get to work. The programmers continue refining the low-level designs until they know exactly how to implement these pieces in code. In fact, one of the famous development techniques, you basically just keep refining the design to give more and more detail until it would be easier to just write the code instead. Then you do exactly that. And as the programmers write the code, they test it to make sure it doesn't contain any bugs, or rather they test it to find and remove as many bugs as they reasonably can. In fact, I have found out that there's a testing cup, being held like every year in various locations or all over the globe. So even if a particular piece of code is thoroughly tested and contains no or few bugs, there is no guarantee that it will work properly with the other parts of the system. After a piece of code seems to work properly, it is integrated into the rest of the project, and the whole thing is tested to see if the new code broke anything. In fact, software development has a lot to do with mitigating, bugs and detecting bugs. And let me give you this example. So suppose requirements gathering and high-level design, low-level design, and development works like this. Every time you make a decision, the next task in the sequence includes 2 more decisions that depend on the first one. So this figure from Rod Stevens' Beginning Software Engineering shows this. So for example, when you make a requirements decision, the higher level design includes 2 decisions that depend on it. Well, this isn't exactly the way it works, but it's not as ridiculous. And suppose you make a mistake during requirements gathering. So for instance, the customer said the application had to support 30 users with a 5-second response time, but you heard 5 users with a 30 seconds response time. If you detect the error during the requirements gathering, you need to fix only that one error. But how many incorrect decisions could depend on that one mistake if you don't discover the problem until after development is complete? So the answer here would be like 15. So at least an order of magnitude more, but the core is that the longer a bug that remains undetected, the harder it is to fix. And this figure basically shows how the potential mistakes propagate. The last piece here would be the so after you've built the next blockbuster first-person shooter, financial projection tool, or goat simulator, it's time for deployment. So deployment is the process of putting the finished application in the user's hands. While this seems like, copying files between computers, deployment can be difficult and time-consuming and expensive. For example, suppose you've written a new billing system to process payments at stock exchange for millions of people. And as soon as the users start pounding away on your software, they'll find bugs. This is another software axiom. Bugs that were completely hidden from testers appear the instant users touch the application. Of course, when users find bugs, you need to fix them. As mentioned earlier, fixing a bug sometimes leads to another bug. So now you get to fix that one as well. And if your application is successful, users will use it a lot and they'll be even more likely to find bugs. There's one more important thing that you should, do before you jet off to Cancun. You need to perform a post-mortem or a wrap-up. So you need to evaluate the project and decide what went right and what went wrong. You need to figure out how to make the things that went well occur more often in the future, and you need to find out how to prevent the things that went badly in the future. Just wrapping up, software development lifecycle has to do with performing more or less the same basic tasks, that is requirements gathering, architectural design and low-level design, development, testing, deployment, and maintenance. And different development models have been created that handle these basic tasks in different ways, such as making some less formal or repeating tasks many times. And the basic tasks often occur at the same time, and some developers are working on one task and other developers work on another task. So work sometimes flows backward, with later tasks requiring changes to earlier tasks. Fixing a bug can lead to other bugs. The longer a mistake remains undetected, the harder it is to fix. So that concludes this first shorter module on software development lifecycle, and I see you in the practice.